second kind of data and the corresponding neural network architecture, right? So we're now talking about text or sequence data, right? And the corresponding architecture we're going to talk about is recurrent neural networks, okay, or RNNs. So last time we talked about CNNs, right? So we said that, you know, if you look at how ImageNet has enabled the development of computer vision models, right? Especially CNNs, right? We have seen that, you know, from the AlexNet, right? This is 2012, we see the first big major improvement that was, you know, thanks to the AlexNet. But I also reminded you, I think I used one slide to tell you that the first CNN by Yang LeCun or LeNet was in late 80s or early 90s, as I recall. So the question is, you know, apparently they didn't have contributions to earlier ImageNet. Then what happened, right? So I think I used some slide earlier to tell you why that was the time, year 2012, was the time for CNNs to ripen for computer vision, right? One is, you know, the hardware and this vectorization, you know, GPU tensor calculation gets much more effective. But there's also another fact that is, you know, these neural networks are data-driven, and you need high-quality data, right? ImageNet actually provided a lot of, you know, high-quality data that has hierarchical labels, right? So, and over the years, you know, starting from the AlexNet, we see a lot of improvement, right? So, including the VGG in year 2014, right? And this is what VGG 16 or 19, right? Then you also have the GoogLeNet in year 2014, right? So, you know, then this is the performance, right? And if we compare them to the human error, actually they even outperform human errors, because sometimes for a random human, it's really hard for you to find out some fine labels, right? For instance, you may not know well the difference between two breeds of dogs, right? Some of you know well, some of you don't. So, but for computer models, as long as they have enough examples, they can learn that very well. So, you know, this revolution of depth, right? So we see that these models are, you know, getting deeper, but there are more things, right? So for instance, the residual blocks. If you recall, last time I talked about the treatment of protein sequence data and the corresponding features as image, and also the task of contact prediction as a pixel level segmentation, image segmentation. Because each row is a residue index, each column is a residue index. So that is artificial image at the end that we need to figure out at each pixel the corresponding label being 1 or 0 for residues being contacting or not. Or you could even use two channels. One channel is the distance, one channel is the distance expected value, one is the channel, one channel is the distance standard deviation, or something like that, right? So it's like the image task of pixel level segmentation. Back then, they already used the residual blocks back then, right? So the residual blocks is allowing you to have these identity operations, right? Bypass these kind of jump connections, right? And you can use these blocks sequentially in this ResNet, right? So that's what the ResNet. And there's, of course, in 2017, there is SENet, right? So if you're interested in, you can look into them into more details. So now, let's look at what complexity brings in, right? So is this just a game of bigger and bigger models, right? Let's look at some analysis, right? And let's see what implications we reach. So this is the top one accuracy for different models, right? The higher the better, right? And you see that starting from the AlexNet and all the way into later like ResNet, VGG, ResNet, and Inception, the accuracy level is increasing. But now let's compare, right? These accuracies still the y-axis, but now let's change the x-axis, right? Instead of ordering these models, in a scale-free way, now let's order the models x-axis by the number of operations, right? By the number of operations. In the meantime, the dot, or the point here, right? We have the coordinate of the number of operations versus the accuracy, right? In the meantime, we also can, change the radius of the dot based on how many parameters we have. For instance, the VGG16, right, has about 125 million parameters, right, and so on, right? So now we can compare the performance versus the model complexity. But of course, as I said, counting the number of parameters is not the, right away, right? But the number of operations is something that we can calculate all the time, and the number of parameters, that's something we can figure out. But whether it's too complex or not, that is relative to the data, right? So AlexNet is here. Is actually here. It actually have 60 million parameters, and the accuracy is not that high, right? And but the number of operations is not that high either, right? So you see that the later networks, such as GoogleNet, ResNet, right? So they still don't have a lot of parameters because they keep reusing some building blocks of the same parameters. So they do have these parameter sharing ideas kept used, right? And operations increase a little bit because you still have to compose these repeating units together, right? And then you see some other cases like Inception. Inception's number of operations and the number of parameters are both very high. Then VGG is even higher in both the number of parameters and the number of operations.